So what about the reaction between organometallic reagents and type 2 carbonyls? Remember, type 2 carbonyls were esters, acid chlorides, amides, carboxylic acids, etc. Well, let's take a look. So the reaction is different. However, since carboxylic acid derivatives contain a group Z, again, this can act as a leaving group. So you got to remember that type 1 doesn't have a leaving group. Type 2 has a leaving group. That's very, very essential to recall. This is the main difference between them. So let's take a look. So imagine we're reacting this ester with the organometallic reagent, in this case CH3 MgBr. So let's draw out the bond. Always draw out the bond between the carbon and the magnesium or the lithium, etc. So we know the first step is the attack at the carbonyl. Making the tetrahedral intermediate. Minus. Now, remember, this is Z. So the question is, do we have a leaving group in this reaction? We do. So we have a leaving group in this case. So again, this is a tetrahedral intermediate. And we do have a leaving group. This is very important. So the electrons are going to come down in our leaving group. What is its job? To leave. Very well. So look what we're making now. You should be able to draw this very easily, the product. So what is the product? What functional group is that? If this leaves, then I have the carbonyl bond, and then I have the CH3 and the CH3. So we have a ketone. So this is a ketone. Now we can't stop here. Can't stop here for two reasons. Organometallic reagents are highly reactive, Grignard reagents. Plus we have a ketone here. So we can't stop here. Just like when you did the reduction before, ketones are more reactive than esters, what we started with. So while doing that, I left no room for me to draw the Grignard reagent, but we will. So let's put it here. So there's going to be another attack, another round of attack here. Okay. Okay. So again, we need to protonate this. So if we have H2O, as the second step, then we're able to protonate this and finish with the alcohol. Now, it's essential to remember a few things here. Is you must use 2 equivalents or moles of Grignard's reagent. So this one, stoichiometry is important. That's number 1. If you only use 1 mole, 1 equivalence or 1 mole, you will get 50% conversion. So you won't get a full reaction. So be aware of that. In order for you to produce an efficient, a high yield reaction, you have to use 2 moles. If you use 1, you will get a 50% conversion. So you will get a lot less because you run out of material. So you will get some of it as a ketone, and then of course some of it as an alcohol, which is not a very efficient reaction. Now, let's get this here. Let's go to the next reaction. So what about organolithium? Same thing happens here. This is an acid chloride. It's even more reactive than an ester. Attack happens. Okay, so do we have a leaving group? Yes, we do. As a leaving group. This is our leaving group. So the electrons are going to come down from the carbonyl oxygen, kick the Cl out. And you're going to produce a ketone right there. Now, you should stop here because ketones are less reactive. So I'm going to write it down here, write it at the top here. Should stop here. But, or because acid chlorides are more reactive than ketones. because what we have is a ketone here, so reaction would stop. But it does not. But the problem here is that reaction will keep going because organolithium reagents are very reactive. So here it is again, like the last reaction. And here we go. So you will end up with a tetrahedral and of course you will protonate and end up with this. What's up with this? The alcohol, of course.